Priano Productions presents Nova number 607, The End of the Rainbow, which is unclear fusion. GBH TV, Boston.
This program was produced by WGBH Boston, which is solely responsible for its content. Major funding for Nova is provided by this station and by other public television stations. Additional funding is provided by grants from TRW and the National Science Foundation.
Nuclear fusion, the energy which fires the hydrogen bomb, and the sun. Could this be the pot of gold waiting at the end of the rainbow to provide energy which is cheap, clean, and inexhaustible? Controlled fusion energy for all mankind. Fusion energy has powered the sun since its beginning. On Earth, it is more recent. The hydrogen bomb, nuclear fusion energy uncontrolled. Since the hydrogen bomb dwarfed the atomic fission bomb, scientists have dreamed of controlling fusion energy, harnessing it to man's needs, freeing him from limited oil supplies. The radioactivity of present-day nuclear fission power. The uncertain economics of solar power. The pollution of coal. Every drop of water on Earth carries the fuel for controlled fusion energy, deuterium, an isotope of hydrogen. It's cheap, clean, non-radioactive, and inexhaustible. But the fusion process which could burn it has yet to succeed. This water contains 100% deuterium. Its fusion energy equals 30,000 gallons of gasoline. Can this golden prize ever be delivered to man?
Oh, there's been such an enormous change over the past few years that, we really think it's almost in our hands. We can almost feel it.
My view is that fusion is an alternative that we cannot really count upon. We cannot base energy policy on the commercial realization of fusion at any specific time in the future. But let's keep working on it. Could be very important.
The only options we have for the long term, really long term, are solar power, nuclear fission with breeder reactors, and controlled fusion. And none of those are in the bag.
I'm very optimistic that we will demonstrate the scientific feasibility of fusion. That is, we can produce the conditions of temperature, density, and confinement time that are required to sustain the fusion reaction.
I think it would be disastrous to have an energy source of that kind, because our track record in responsibly managing big sources of concentrated energy is not really very good.
Nobody knows. Certainly not those people who say they know. It could be very important. It could be not important at all.
Dependency on foreign energy today haunts Washington and the whole nation. Successful development of fusion could, in the long run, help relieve this problem. shouldn't clear governmental action be devoted to achieving commercial fusion power now? Don't we need it desperately? Yet, should this generation be asked to gamble that fusion might work for some future generation? The research is costing the taxpayer $480 million this year, over $1 million a day. Are we prepared to play such high stakes that fusion can, might, or even should be considered as a possible long-term answer to our energy crisis? The nuclear power plants we know today use fission, in which uranium or plutonium atoms are split to create energy. These fission atoms are unstable, and it's not too difficult to set a fission reaction going. With a particular arrangement of the nuclear fuel, it's possible to sustain a controlled fission reaction and generate electricity. And barring accidents, controlled fission works, though it leaves highly radioactive fuel waste, which is a problem unless it can be stored with adequate safety. Electricity could also be generated without radioactive fuel waste by fusion, as on the sun, fusing together the nuclei of light atoms, hydrogen or its isotopes, deuterium and tritium. But fusion isn't easy. It needs a great energizing force to set it going. On the sun, it's the force of solar gravity that does it. But on Earth, gravity is puny. Even the uncontrolled fusion of the hydrogen bomb needs an atomic fission bomb to set it off. And until fusion can be controlled, it cannot give us electric power. What then is the science behind the problem? Hydrogen nuclei have a positive charge, and they repel each other. They must be smashed together at tremendous speeds, at temperatures near 100 million degrees, to fuse, to create a helium nucleus, while a neutron flies off with enormous energy. This neutron energy could be converted into heat, which could be converted into electricity, controlled fusion power. Attempts to master this process started in the 50s.
The early 50s were a marvelous time for fusion, when the physicists were in charge and they had the feeling that if they just did the physics right, then they could maybe give the job to an engineer who would then build the device in a few weeks, or to some theorists, if they wrote the right equations on the board, just like drawing a pentagram on the floor, the whole device would appear full-blown before them.
Work to control fusion began in many countries in the 50s. In America, at Oak Ridge, Los Alamos, Princeton, Livermore, MIT, and elsewhere. The prospects were exciting. The prize, tantalizing. Of course, the fusion process did require enormous energy to heat the fuel to 100 million degrees. And, as this Russian film shows, a heated gas ionizes, stripping electrons from their atoms, making what is called a plasma. So the first task was to devise a way to confine a plasma while you heated it to fusion temperatures. No physical material could contain it. But the theory was that a very strong magnetic field could confine a plasma in space, away from the material walls. Then just heat it to the right temperature and density for long enough, and you could achieve magnetic confinement fusion. But plasmas, as they warmed, became unstable. They gyrated, kicked, and squirmed away. They refused to be magnetically confined. So before you could control a fusion process, you had to learn how to confine plasmas, how to hold them long enough in space and densely enough while you heated them. It was a whole new science, and despite periodic breakthrough claims, little real progress was made, until the Russians in the early 60s managed to overcome some major plasma instabilities with a machine in which the plasma bit its own tail. A tokamak, a donut-shaped device in which additional magnetic fields generated an electric current in the plasma, stabilizing and heating it, at least for a fraction of a second. It seemed a big breakthrough, but many other instabilities blocked the way to quick progress. So, for nearly 30 years, scientists have been trying to confine a plasma for 1 second at a density of 100 trillion particles per cubic centimeter, as they heat it to 100 million degrees. And each beginning has usually become a different kind of failure. Nevertheless, a great understanding of plasmas accumulated. It started back at scientific fundamentals and worked forward to the threshold of paying off. As back in 1971, the director of the fusion program announced, "It is no longer a question of if fusion will work, but when." Today, at Princeton University, optimism is high among scientists working with their tokamak Princeton Large Torus. In August 1978, results from their experiments made headlines across the world. These were hardly the first such headlines in 30 years. Major breakthroughs had been proclaimed before. And this time, the French had the goal to add to their story. It should be seen in the light of the ferocious struggle for grant money in which the American laboratories are involved. A touch of cynicism, perhaps, for the results did have a meaning.
The results of last August, when we actually achieved temperatures of 75 million degrees, were of enormous importance to us because it relieved a principal uncertainty that had been bothering us, namely, would the plasma become turbulent at these high temperatures?
Important? Yes. A breakthrough? No. The media were making news from yet another Department of Energy leak at appropriations time. Oversell has been pernicious in fusion. How many of the claims can be truly significant?
At times, fusion was oversold, unfortunately. And often it was claimed that some great breakthrough is just around the corner. And there were so many corners that they were describing a different geometrical universe than the one we live in. But these days, the realization of the complexity of the whole energy problem has brought to fusion and other energy areas a kind of degree of realism. And we find it growing day by day.
Yet, even now, immoderate headlines can do a disservice to fusion, distorting today's achievements on what still remains a long road ahead.
On the basis of those results, we confidently predict that the next phase, now under construction, the TFDR, will indeed achieve break-even.
Break-even, or scientific feasibility, is fusion's first goal, expected by the Department of Energy by the mid-'80s. Energy out equal to energy in. Technological and engineering feasibility would be the next stage, at the beginning of the 21st century. More energy out than in, with some of that energy converted into electricity. Economic feasibility would be the third stage, a pilot plant working reliably and economically, perhaps 10 years later. Yet, if all these stages succeed, it could still be 30 more years before fusion energy could make a nationwide impact. Here at Princeton, the construction of the experimental TFTR, tokamak fusion test reactor, will open the way, it's hoped, to break even in the early 80s. Energy produced equal to that consumed, to force the plasma fuel to the critical temperature, density, and time conditions of burn. Yet this tokamak will be a scientific tool only, producing no usable energy nor solving any of the engineering or technological problems of a power reactor. Costing $239 million, TFTR will mark another escalation in the search for the grail of controlled fusion power. Tokamaks are closest to achieving scientific break-even. Yet, are they necessarily the best bet to develop for a practical power plant?
Some people have suggested that the tokamak approach to fusion is a dinosaur in the sense that it would be exceedingly unwieldy and very unsuited to the broad environment in which it would find itself. That is, it would be too big, it would be too difficult to maintain, it would be too difficult to keep going for an electric utility, for example, to want to buy it.
I think a tokamak is probably the lowest risk route to finding out whether we can burn fusion fuel in a magnetic field. I know a lot of people are less than enthusiastic about engineering it into a reactor. But at this point, I guess I would wait to see how the physics comes out and look at it, and then do some engineering studies before I made a decision.
Clearly, it is possible to make a machine that uses the tokamak principle and could provide power if we're lucky. The difficulty is that this has to be a machine that works day in and day out on a power grid, connects up to this kind of a facility. And that means that it has to be one that can be operated in a practical, commercial way by the utilities.
And while the tokamak leads the way toward the first stage of scientific feasibility, its design may prove too complex for the ultimate goal of producing economic fusion power. Perhaps this is why the utilities have put so little money into fusion research as a whole. Most of the research money comes from the government. The Department of Energy funds various fusion projects. The tokamaks are only one approach. There are some totally different ways of trying to achieve controlled fusion. One whole rival area is called inertial confinement. Instead of working with a plasma fuel, which you try to hold magnetically while you try to heat it to fusion, in the inertial approach, you put the fuel, a mixture of hydrogen isotopes, deuterium and tritium, into a tiny pellet. Then zap this fuel pellet with enough energy in 1/1,000,000th of a second to compress and heat it to fusion. This is the way the hydrogen bomb works. This is inertial confinement fusion. The zapping is done with lasers or electron or ion beam drivers focused onto the tiny target in a vacuum chamber like this. Here at Los Alamos, the Helios machine is an experimental device. The target pellet has to be set up by hand. Then, safe in the control room, the scientists set up for the shot.
Okay, let's fire. Let's fire a full shot at 46 kilowatts.
Okay, front end, are you ready? Ready. Beam diagnostics, are you ready? Ready. Okay, we're beginning the charge sequence.
For 1/1,000,000th of a second, as much energy as the whole United States can generate will be blasted onto the target, attempting to compress it to a fraction of its size and heating it to millions of degrees. In that instant, part of some of the densest, hottest mass ever created on Earth will fuse.
That's right on the nose with the other one.
That's it.
Electrical data looks normal.
What's the impedance?
Impedance is running about 3.2 ohms.
Okay.
Okay, we're charging the electron beam. We have about 30 seconds.
E-beam's 55?
55. 10 seconds. Ready to test. 3, 2, 1. Good shot.
A miniature hydrogen bomb explosion. This is inertial fusion. But it still needs vastly more laser driver energy to zap the target than the actual fusion energy given out by the explosion. Any projected power reactor must probably require 10 energy-gaining explosions every second. In the high deserts of New Mexico, major programs in inertial fusion are carried out at government-funded national laboratories, at Los Alamos and Sandia, as well as in California at Livermore. The national laboratories do military weapons work as well, conducting experiments on nuclear devices, on death ray laser and particle beams, and on the neutron bomb. This is a model of Shiva, a 200-foot-long, 20-laser fusion machine at Livermore. Here, classified research in inertial fusion is concerned with weapons design and effects. Unclassified work goes on in trying to make inertial confinement fusion a practical power source for the future. This is the target chamber section of Shiva, 60 feet high. A utilities man was reported to have laughed at the idea that this machine could be the forebearer for a practical power plant.
Well, what we're trying to do here is show that a laser can compress thermonuclear fuel up to high densities and high temperatures and begin to start to get it to burn. There is not an issue as to whether or not a laser can be built big enough to drive a reactor, or whether an accelerator can, or an electron beam machine. What is the difficult issue we face in this program is to prove the thermonuclear weapon physics can be scaled down to something that's half the size of a child's marble and still be efficient. The chief goal of the program is to prove that that's possible.
Nevertheless, the present Shiva machine must be expanded to double its size for $195 million before it could try to achieve scientific feasibility, as much energy out as needs to be blasted in. That may happen by 1986, but then Shiva's future would be limited, for the glass lasers it uses aren't efficient enough to go beyond the present test tube stage of inertial confinement. The money, energy, care, and craftsmanship of glass laser work belong to this present stage of trying to achieve scientific feasibility only. For while the glass laser delivers a concentrated punch to the target pellet, the huge laser beams can't be fired in rapid succession, and they take up so much energy that the fusion return could never be economic. A rival approach, the gas laser, consumes much less energy, but its punch on the target pellet seems less effective. Its wavelength may prevent it from zapping a pellet efficiently enough. Electron or ion beams are another alternative. Cheap, simple, and efficient devices.
Bill, needs to go about 3 millimeters to the left, please. All right.
But they have focusing problems and various other technical drawbacks.
A little more. Fine. Okay.
An ion beam punched this hole in a steel plate, but that doesn't mean it could also produce successful fusion. Can the program to harness inertial confinement fusion power work practically?
I think the scheme of trying to harness very small nuclear explosions doesn't pose a problem of bombs or things of that kind, but it does pose the problem that the duty cycle, the time that the device is giving you energy is very small, and as a result, its power per dollar, if you like, or power per unit of effort you put into it will be quite low. And also the technology looks very difficult to have an experimental arrangement a couple of 100 meters long, aiming at something that's 1/10 of a millimeter or less, and have all this thing happen time after time after time without losing alignment.
One has tremendous difficulties in building lasers that not only have the required efficiencies, or electron beams or ion beams as alternatives that have the required efficiencies, but these things must be able to operate thousands and thousands of times a day for years without failures, without extraordinarily expensive maintenance, without the enormous quantities of energy running around through these devices just destroying the machine itself. These are exceedingly difficult problems, and I think we have to expect to take decades to solve them.
Inertial confinement is the way a hydrogen bomb works. And as I think everyone knows from the experiments in the Pacific, hydrogen bombs do work, and they do burn fusion fuel very efficiently. That's the only way man has ever made it work efficiently on the Earth.
Exploding microhydrogen bomb pellets raises the weapons proliferation question. Knowledge of this work could allow others to build bombs. Therefore, much of the work is classified. Could this be holding back the effort to develop commercial fusion power?
It is classified today because of some of the physics similarity with thermonuclear weapons, and the Carter administration is very concerned about proliferation. But let me give you a couple of examples. Magnetic confinement fusion was originally classified And when it became in the interest of the country and the world to have it declassified, it was. If we look at nuclear reactors, the first ones started out as production facilities for plutonium for weapons and were highly classified, were then declassified so the Navy could use them in submarines, and then fully declassified so that people could build power plants out of them. I would expect that inertial confinement fusion, once it showed its promise as an energy source, would certainly be declassified, if not before.
I certainly wouldn't argue that classification should be lifted on inertial confinement fusion work, because if the links to nuclear weapons are genuine, then indeed one wants to protect that information to avoid the widespread dissemination of insights relevant to the construction of nuclear weapons. It would be nice to declassify if there were nothing there to protect, but on the assumption that the classification lid is there for a reason, I think one has to worry about whether research on this technology should be propagated at all.
I don't think much of the classification of anything. In the case of inertial fusion, it makes no sense whatsoever. It is based on an overly narrow view. It is based on an imagination that if we are only determined enough, we might classify the multiplication table. Of course, if we ever succeeded in doing that, it would slightly hamper scientific development.
Does it show prudence to keep inertial fusion work classified? Or is it merely slowing progress in international cooperation in the name of an empty threat? Aren't there enough problems with the fusion effort anyway? Magnetic confinement has difficult questions with the tokamak, its leading scientific contender. In inertial confinement, the scientific leader, using the glass laser, has a decidedly limited career on the road to fusion power. Could the goal of controlled nuclear fusion be beyond reach?
Fusion has been faced with a series of problems through its history, each one of which at one time was thought to be unsolvable. And one at a time, these problems have submitted to the pressure of our push in terms of technology and science. And we have been successful at solving many of these problems. In a sense, you could call these miracles. We haven't seen the end of the road yet, and I'm sure that there will be more of these advances, miracles, if you will, before we're finally through.
Miracles are expensive. The Department of Energy expects a total of $20 billion in present-day dollars to be spent on fusion research in the next 20 years. And if fusion has not been abandoned by then, it will still be 5 more years before work would start on a pilot demonstrator reactor. Would the Wright brothers have gotten such support by promoting jumbo jets 4 or 5 years before they had built a machine which they were willing to predict might actually get off the ground? We know that there were many approaches to flying before the Wright brothers did get off the ground. Fusion is in the pre-flight state today, pre-scientific feasibility, but most experts agree that in the next several years, fusion will take off. But which fusion model will be the best bet in the long run? There are a variety of scientific approaches, rivals, in both the magnetic and inertial fields, each competing for funds with its own claim and its own particular problems, like so many of the early hopeful attempts in flight.
This is, until recently, the only machine of its kind in the world. Another machine...
The Bumpy Taurus is a tokamak-type machine with distinctive geometry and improved magnetic efficiency.
The most important thing is to prove that the basic concept is correct, which is a concept of a long pipe
This mirror machine will hold a plasma in a straight cylinder, a rival to the circular tokamak. It could be less complex to develop.
As you can see, doublet has a very tall magnet.
The doublet is a tokamak variation with a special plasma cross-section. It could be a dark horse, the first to reach break-even.
The Alcator experiment was based on the idea of using very high magnetic fields, much higher than had ever been used before.
This tokamak holds the world fusion record, the highest simultaneous conditions of temperature, density, and time.
The construction site on which we are standing is the site for the Antares laser.
This will be a carbon dioxide laser machine, which might succeed the glass laser. Yet, does it make sense to develop such a profusion of machines, all at the same time?
Well, we're looking at fusion with various approaches. And I think that's very important now to have this broad range of approaches, because some of these approaches, I hope not ours, will run into that unsolvable problem that we can't go around. And at that point, we're just going to have to say, okay, we've gone as far as we can with this approach, we're going to have to stop.
Well, of course, the airplane did fly. Then it took 70 years of engineering and technological problem solving for flight to make its present worldwide commercial impact. It could take fusion as long, after it has achieved break-even. The most advanced of today's fusion machine concepts are still experimental scientific devices. Enormous problems must be surmounted in progressing from these to an economically working fusion power plant. What are the problems? Can they be overcome? A successful fusion reaction for a power plant must probably take place in an inner vacuum reactor chamber. The fusion process will throw out a great flux of neutrons traveling at near 20,000 miles a second. These must be trapped in a blanket. Here the neutrons would give up their energy as heat. The heat would be transferred by perhaps circulating helium to drive a turbine, which would drive an electric generator. Meanwhile, in the blanket, the neutrons would react with lithium to breed tritium, the radioactive hydrogen isotope, which must be specially recycled as fusion fuel. The reactor must be made of material which can survive the enormous radiation and heat flux, especially the first wall and blanket nearest the reaction. This whole core will become highly radioactive, repairable only by remote control. Today, the fusion power reactor is a design concept only. None could be built. None of the necessary technology exists. The crux of the fusion debate is whether a reactor could ever be built to work economically. What are the key roadblocks to practical fusion power?
On the magnetic side, there are the problems of fueling and heating the plasma. There are the obvious problems of radiation damage to the structural materials. There is the problem of extracting tritium from the breeding materials. And then there is just the overall general problem of trying to couple superconducting magnets with very high temperature coolants and even hotter plasmas. On the inertial confinement side, there is the development of the drivers, which would be either a laser or an electron beam, a light ion beam, or a heavy ion beam. That is not clearly established yet. The physics for the implosion of the pellets still needs some work. And once we understand that, then we have somewhat the same set of problems in terms of radiation damage, extraction of tritium, and of course coupling with the rest of the power plant.
One of the technological problems that fusion must face is to find a way to convert the energy output into useful form, and secondly, to find a way to regenerate the tritium fuel, which early fusion reactors will all require. This will be done in something called a blanket that surrounds the core of the fusion reactor and must serve all of these functions at once. It must transform the energy output of the fusion reactor into a form that can be used to generate electricity. It must regenerate the tritium and permit it to be recycled into the reactor core. These blankets could be very awkward. They would likely be filled with lithium in some form, which is a quite toxic and intractable compound, and they would be quite complicated geometrically, because one has to have holes in the blanket for the fuel to be injected, for various kinds of controls to penetrate, and so on. So the blanket is a very technologically awkward part of the fusion reactor problem.
Laboratory work at the University of Wisconsin is examining one most critical aspect of the blanket problem: how materials, especially those of the first wall, would hold up to the intense radiation and heat which would occur. Specimens which have been intensely irradiated are prepared for metallurgical examination. Electron microscope results indicate that in a reactor, every atom of the chamber material might be displaced 15 times during 1 year of operation. Such massive stress must suggest ominous maintenance requirements for the inner part of the reactor, which would also become highly radioactive and require safe storage for perhaps 50 years after the reactor is decommissioned. There are some ideas for solving the maintenance problem.
The first wall problem is a fundamentally difficult problem for all fusion reactors. We have designed a fusion reactor without a rigid first wall, where the first wall is liquid lithium a meter thick, and it can sustain damage, of course, and repair itself because it flows. So we think we have a conceptual solution to the first wall problem.
Even if this were feasible for inertial confinement, it's not for magnetic confinement. Here, the complexity of magnetism and geometry needed to hold a plasma in space would rule it out. The radioactive first wall would have to be maintained by remote control. This device is part of a mock-up of the Princeton TFTR, due for operation by 1981. But remote maintenance of an actual power reactor will be very much more complex, and development must await the later engineering stages of the fusion program. The technology of fusion development is awesome. Is it even now heading in the appropriate direction?
One sometimes wonders whether we can trust the technologists to do absolutely the right thing, to build the sort of device that the society really wants. I am myself a technologist, so perhaps I have a bias here, but my view is that the process of developing a technology like fusion must draw on all kinds of expertise outside the technological community as well as in it, to be sure that the process leads to a device that society really wants. Otherwise, you could end up with another supersonic transport.
Fusion must avoid the environmental and economic drawbacks associated with a supersonic transport. Even if fusion can overcome the enormous problems outlined in this film, it should be made to work only as an acceptable technology. Mounting misgivings, it seems, prompted the Department of Energy in 1978 to reassess the whole fusion program.
And last year, we thought it would be useful to form an ad hoc outside group of experts, chaired by John Foster, to give us an overview of the state of health of the program and its prospects.
But was it the health of fusion research work, or its euthanasia, which they had in mind? Informed sources have said that the Department of Energy was ready to transfer fusion money to other energy programs. They expected a negative report from the ad hoc committee to back up that policy. They were taken by surprise. While somewhat critical of the program's emphasis, the committee strongly endorsed fusion work, and the Department of Energy made certain policy changes, but kept funding at its present level.
Well, the committee found, at least in its judgment, that the program seemed a bit risky. As a program being conducted not so much now as a scientific effort in search of scientific goals, but one that is a scientific and engineering effort directed to national needs, it was a little risky. A little too much emphasis on one aspect, and the committee urged that more effort be placed on other possibilities so that if one doesn't work, we've got a good start on another.
Well, we have certainly made a variety of changes which were suggested by the Foster Committee and by our own deliberations. I don't know that we've covered every base. I'm not sure that we would agree with every base, but we have made a number of adjustments in the program as a result of the advice of that ad hoc experts' recommendations.
The Department of Energy has now stretched its timetable for fusion development and broken it into stages. The first stage involves alternatives in both the magnetic and inertial programs, leading to a choice of one single machine from each branch, until either the inertial or magnetic line would be dropped. During the engineering stages, the survivor would become the engineering power reactor. If all this has succeeded, the final stage, well into the 21st century, would be a demonstrator reactor, the pre-commercialization phase. This series of decision points and extended finish line represents the reassessed Department of Energy fusion policy.
I trust that the cause of the change in the Department of Energy's policy was a recognition that by hurrying too much toward fusion, one might throw out the characteristics of the technology that make it attractive in the first place. I think this finally became apparent, in part because of the efforts of various scientists around the country who pointed out the things that could go wrong if you hurried too much, and in part because the electric utilities themselves made their views known on what sort of machines would be necessary to be attractive to them as users.
Proponents still point out that we got to the moon in 10 years with an all-out crash program. Isn't controlled fusion energy as important as the moon? Could a crash program work now?
I would like to say to you that it is very unclear that a crash program, particularly at this stage of development, is the right way to go. We're without any certainty here that a much more rapid amount of pace or amount of money would really be all that important at this stage.
The Department of Energy's program, up until a few months ago, I think too closely resembled a crash program. It posed the danger that one would build a fusion machine too soon and as a result get a machine that perhaps no one wanted. The present timetable is much more reasonable, I think, is not a crash program, and thus will avoid the liability that a crash program has, which is that you won't have a program, but you will have a crash.
The problem is, I think, the following one. When you come from the media like yourself, if something happens at 9 o'clock in the morning, you want it to be all finished by the evening news, or certainly by Friday's evening news. Fusion is more like raising a child. It takes 25 to 45 years to find out whether or not you did a good job. Now, as you go along and the kid learns how to read, you're very enthusiastic about it and you tell people. And when the kid, gets into a good college, you're very enthusiastic and you tell people. That's what we're doing here today. We're talking about learning how to read. But it's that long a problem.
Whatever is the present or future status of fusion, its relevance lies with the coming generations. It would be their pot of gold, not ours. For by the year 2000, the large-scale energy alternatives will be coal, solar power, nuclear fission using the breeder reactor, and fusion power. We will not, in this film, examine the prospects of these energy alternatives in detail, but we bring them up to try to put fusion into a broader energy perspective. Coal is abundant enough, but burning it could create serious environmental and health problems, and the threat of excessive carbon dioxide in the atmosphere, distorting the world's climate. Solar energy is inexhaustible, but intermittent. It could be expensive, inefficient, and labor and materials intensive. Fission power, involving the breeding of new fuel, could be virtually inexhaustible, but will have the problem of radioactive waste disposal, the chance of catastrophic accidents, and the constant danger of stockpiles of weapons material, which might be impossible to completely safeguard. Controlled fusion power is the only option which has never worked. And while all the energy alternatives might be developed as an insurance policy, fusion and the fission breeder, both large and expensive to develop nuclear technologies, do seem to square off against each other.
I think the motivation for developing fusion in the first place is that none of the alternative inexhaustible energy sources are completely satisfactory. The fission breeder reactor could run civilization for hundreds of thousands of years, but carries very heavy environmental and social liabilities in the form of the toxic dangers of plutonium and in the form of the threat of proliferation of nuclear weapons and the threat of nuclear terrorism associated with a large electricity economy that is based on this very dangerous material, plutonium.
In my view, the risks incurred in having the breeder and not needing it are smaller than the risks incurred in not having the breeder and needing it. It is therefore my view that we should go ahead with the breeder development with, what shall I say, all deliberate speed.
Let's be a little more specific. The Soviet Union has a rather modest program of fast reactors, which at the moment don't breed. They hope they'll breed later. And of light water reactors, and the same is true in Germany, France, Japan, Britain. But there's really quite substantial doubt whether, for example, the next fast reactors in Britain and Germany and even in France will ever get built for very fundamental economic and political reasons. It's also clear that economically they're turkeys. The only reason for building them would be prestige and the momentum of the program.
I believe that in many ways fusion has an advantage over breeders because the problems of radioactive waste associated with the breeder, particularly a plutonium-based breeder, are much more severe than with respect to fusion reactors. While fusion reactors also have radioactive waste problems, they're of a much more manageable form.
Yet, is the choice of how to produce more and more energy the only question? Shouldn't we also be examining whether there really is an energy crisis? Could conservation and simple localized existing energy sources completely eliminate the need for large-scale fusion or fission breeder power altogether?
What we ought to be doing is what I call a soft energy path. That has three elements. One is to use much more efficiently the energy we've got. Another is to use fossil fuels intelligently for a transition to, thirdly, dependence on what I call soft technologies, that is, diverse renewable energy sources, which are fairly understandable to the user and that supply energy at the most effective scale and kind to do each job.
I think that it is most dangerous to kill nuclear energy today, as some people are wanting to do, on the grounds that the soft technologies based on the sun are able to take over the entire energy burden without causing vast social unrest, vast social difficulties of a kind that we simply can't fathom at this stage. And I think it's irresponsible to suggest that soft technologies can take the place of the existing hard technologies.
Soft energy paths rest, I think, on a realistic view of human nature, not a utopian view in which it's supposed that people are perfectible. I think people are fallible, sometimes irrational, occasionally malicious. We ought to take those things into account and have relatively forgiving technologies. It is sometimes said that insulating your roof involves dramatic changes in lifestyle, but having a plutonium economy doesn't. I don't think that's right.
This advocacy comes from soft heads. It comes from people who have forgotten about the poor billions. It comes from elitists who want their own little dreams come true, and many of whom are scared of nuclear energy without any good reason whatsoever. The people who suffer are those in India, in Africa, in South America, billions of people, of whom these anti-nuclear advocates never think.
If we do not follow the soft energy route, there is one fusion possibility which straddles both sides of the fence: the fusion-fission hybrid. A machine which wouldn't have to overcome the awesome barriers to pure fusion power. It could be used to produce a great flux of neutrons with which to breed fuel for fission reactors.
The fusion-fission hybrid is a device which uses a fusion reactor core to produce very large quantities of fissile material that can be used in fission reactors. This is a worthwhile goal for the fusion program only if one supposes that a large-scale fission reactor economy is a good idea for the world. My personal view is that a large-scale fission economy is not a good idea, that the circulation of these large quantities of fissile material poses temptations to nations to make bombs that are too great, and also poses temptations to terrorists, mobsters, and other dangerous subnational groups to divert this fissile material. Therefore, I personally would prefer to see fusion concentrate on the production of pure fusion energy rather than on the production of this fissile material for fission reactors.
Well, you see, pure fusion that many people like to have may well be half a century away if you want an economically viable program, big program. The marriage between fusion and fission is a very natural one, because fission is strong in energy, and at least in the present form, perhaps a little short in raw material. Fusion is weak in energy, but produces plenty of fast neutrons, which can be easily turned into fuel for fission. So the two go together, and their combination may well become a real, viable economic reality in 15 years. It will take some determination and quite a bit of luck, but it could be done.
I personally think that the issue of a fusion hybrid is a very interesting notion. I think that it has to be considered, should be considered in an exploratory way more than we have in the past. But I wouldn't single that out as having any major emphasis. I just think that it is a very possible notion and one that should be looked at because of all the neutrons that are produced in a fusion reaction.
It's the simplest thing technically to do first. If you can't achieve a really attractively self-sustaining energy-gaining fusion reaction, you can still get an awful lot of neutrons. And if you happen to be very fond of plutonium breeders, then it's a handy way to make lots of plutonium. This is exactly one of the dangers.
Of course, if people are monomaniac and turn up their noses at anything connected with fission, the result will be an unnecessary restriction of their view of what is a practical possibility. On the other hand, if we go ahead with the hybrid, that will give us experience, money, all the things we need to develop pure fusion. Those who want pure fusion should today want the hybrid. Those who only want pure fusion, I think about them like people who want to get on top of the Matterhorn with one single leap. I prefer to walk.
Fusion work is, if anything, long-term. It is one of the options along the hard energy path, none of which has been brought to its decision point. Fusion is the most complex, but the most far-reaching if it succeeds. It is the highest risk, the biggest gamble. Probably it will work scientifically in the early 80s. Yet the key question remains: can it overcome the immense engineering and technological problems on the road to an economic, reliable, and practical power reactor? Can fusion emerge as the pot of gold at the end of the rainbow? Or is it all a false hope?
It has been asked whether fusion could be called the Laetrile of the energy scene. I don't think that's a fair characterization. I think fusion is a technology that has enormous potential, that scientifically it is very solidly founded, and the scientific foundations are getting more solid every day. I think it's important to understand that fusion is not one energy technology, but a great many possibilities. And if the effort is spent, the time and the money, the ingenuity, to develop fusion in its most attractive forms, then I think we can have there an energy source which can make a very substantial contribution to the long-term energy future of society.
Civilizations depend on having food, warmth, things that people need. And that's a dream that could apply to many things, but fusion is just one of the possibilities. One must keep on exploring many, many of these to find a few that work.
I hope for a fusion burn. A fusion burn that would really light a torch, like the Olympic torch, and maybe in 1984. But with it, the dream that with the inexhaustible fuel that's available for fusion, we would have enough energy for the world, not only for our children, but for generations to come.
They are not hopes and dreams, at least in part. They are realities. The reality of a magnificent scientific effort, which has already paid off in more knowledge that will be used in all kinds of ways. Whether it can be used in a practical way for energy, we don't know. In the end, the work on fusion may pay off not only in the beautiful field of science, but also in the practical and urgent field of energy production.
For a transcript, send $2 to this address. This program was produced by WGBH Boston, which is solely responsible for its content. Major funding for NOVA is provided by this station and by other public television stations. Additional funding is provided by grants from TRW and the National Science Foundation.